Hey everybody, welcome to this afternoon's Teardown. My name is Patrick Mannion. I'm brand director for UBM Tech Electronics, including E-Times, EDN, Embedded, Planet Analog, and a bunch of shows, including ARM TechCon. And today we're going to have, we've got two really exciting teardowns for you. We're going to call it a teardown doubleheader for you baseball fans out there. You might have seen the game last night. So we're going to have two devices, and they really are the cutting edge of cognitive computing as well as network surveillance. So the first up on the teardown will be a smart tracker system from iTech Digital Systems, and second up will be the Net Series IP security camera from Innovative Security Designs, aka ISD. So to kick off the teardown, I'm going to start with a couple of introductions for you. First up is Robert Chappelle, CEO of iTech Digital Systems, and Ian Johnston. Put your hand up, Ian. Present. He's CEO of ISD. So before we go any further, I'm going to mention that please stick around for a demo at the end. And if you want to see a demo of these devices, please join Xilinx at the booth thereafter. So we'll kick it right off, and I'll introduce Robert Chappelle. Robert, can you give us a quick overview of how it all came about?
You bet. Our company's been doing eye tracking devices for many years, but we had a desire to move from our old methodology, which was basically attaching a dumb camera to a PC, sending all the imagery to the PC, processing there, and then doing the tracking. We wanted to go to a smart camera format where the processing was done in the camera. So first, let me just quickly review some eye tracking basics. Eye tracking is used to measure the rotation of the eye and ultimately to measure where you are looking. Typically it's on some kind of computer screen, but it can pretty much be on anything. Eye tracking techniques have been around a long time. Over 100 years ago, there were experiments done with photographic film, beams of light, and reflections off the cornea. And we do it very similar today. We use beams of light, reflections off the cornea, but now we use electronic imagers. What's really driving the changes today is the convergence of inexpensive and very capable imaging chips and the inexpensive and very capable processing chips. And we'll show you the hardware in a minute. They're the compact size. So we're looking at eye tracking going from its niche markets of research and disability, moving into many new industrial and ultimately consumer applications. I should mention one thing. The basic idea, if you look at that image in the lower right, is you see the two bright reflections, the pupil, those reflections caused by the infrared, and they provide a reference point under which you can measure the eye rotation. So why did we decide to undertake this project? Well, we wanted to be compatible with a broader range of devices. Our older devices had to run on a Windows PC and nothing else. But if we were going to move to all these new devices, we didn't want to have to shift the image processing burden to each new device and go through that process. So we needed to move it to the edge, as we call it. We also wanted more robust algorithms. We wanted algorithms that could use the power of programmable logic and the added capability that would give. And we also had a requirement to reduce overall power. Many people use these devices in battery-powered devices, especially in the disability market. So there was a lot of challenges with keeping the size down, the power down, those kinds of things.
Do a quick demo.
Yeah. So it's supposed to show the, maybe you should just hold it up. You got it? Okay. Oh, that's a close-up. But anyway, the form factor.
We'll do it up and down, right?
Okay. Let me just hold it in my hand for a second. So the form factor needed to be long and narrow, because with this kind of form factor we can fit it underneath a monitor and it will just slide in there. It's even small enough to fit on many laptops if they have a bezel that will work for that. We also wanted to keep the cost down and the part count down. And the Zinc helped us do that by going to an SoC type solution and ultimately support other operating systems.
Rob, when you're doing the overall design, what sort of challenges did you have when it came to incorporating that much processing horsepower within such a small form factor?
Bill, maybe you could address that probably better than me as far as the hardware design into that kind of form factor.
Yeah, so some of the issues you have to get essentially a single board computer onto this type of form factor. You know, you got the ARM A9s and the Xilinx Zinc along with the programmable logic, and we have a LPDDR2 memory there that allows us to process, and we have a NOR quad-SPI flash, which is our hard drive that we're able to boot from. And trying to get it into this form factor, you know, limited us on routing. We had to go to a higher layer board, so that, you know, we had to be careful in terms of the complexity of the board, and so we had to take more time in that development to keep the cost down. But essentially, it's a very simple design overall with the imager and the memory components in the Zinc, and that's about it. The rest are passives. So, you know, those are some of the challenges.
What sort of tools did you use for layout?
For the layout, we use Altium to support the layout there.
Why Altium?
It was that's what Avnet had used. We were working with to get the Xilinx chip, and we saw a lot of those tools were there. And from what we had explored and stuff, that was for our company, that if we needed to pull it in house, that was a tool that we could really use and afford to help us.
So it's a full 8-layer board. It's a full 8-layer board.
It's an 18-layer board.
18-layer board, sorry, yeah, FR4, and no buried and hidden vias.
No, we didn't have to go to blind and buried, thank goodness, and stuff to keep the board cost down. We were able to route everything we could. Okay. We got a lot of high-speed routing on this as well. So.
What sort of speeds?
With the LP DDR2, we can run up to 800 megahertz. It's a 400 megahertz, 800 megabit rate, and then the image sensor runs at about 245 megahertz, 196 megapixels per second transfer rates.
Okay, and that's not a terribly high data rate. I guess that's because of the use of IR instead of full image processing, using infrared monochrome processing, right?
Well, part of the data rate is just limited by the sensor.
Yeah.
It only comes off of there at a certain rate, but it's plenty fast enough for the applications that we do.
Yeah.
So we can do 60 frames per second, full frame, full 3 million pixels, and do less, cut the pixels down and do higher speed still. So.
Yeah.
Are you the first one to do it off-host?
To do what?
To do it off-host? Do eye tracking using offloading the processor, the main host processor?
I don't think so. I have seen other projects that have been done. I don't know that anyone's done something with that compactness and that kind of power, though.
Gotcha, okay.
This is just a list of some of the key components. We won't read through that in detail, but so the main components listed here, the data flow, just the image sensors, sending out the images continuously at full rate. Zinc is providing both the interface to the image sensor as well as the image processing internally, and we'll talk just a minute about that, what's going on in the image processing. And then it has the high-speed access to the external memory, and ultimately the results are sent over USB. I just want to mention our design process, the development process from the software standpoint. We developed some new algorithms in MATLAB, which we wanted to use here. And initially, we just took those algorithms and put them in, we wanted to move those to programmable logic. But initially, we took our older algorithms, which were running on C in a Windows platform, and we just moved them to the ARM on the Zinc chip. And they compiled with a little work. We got them to compile and run, and At that point where the red line is, at this point we have a working smart tracker. We had it all the older algorithms were running and using just the ARM. The programmable logic at that point was only used as an interface to the sensor. And so we had a working product at that point. But we wanted to include the new algorithms. They're more robust and more powerful. And so we took the step of initially porting those to the ARM, ran about 1 frame per second, much too slow. So then we started moving them to the programmable logic, and now we're back up to the speed. But the thing that we really liked about the process was that we had this flexibility. There's this boundary between hardware and software, and then we also had a boundary between our old algorithm and our new algorithm. And we found that as the project went on, we could use more of an agile development methodology, have a minimal viable product early on, and then we could shift those boundaries around, which we did quite a bit through the development process. We were shifting the boundaries between hardware and software, and between old algorithm, new algorithm. We were able to cobble together pieces as the project went on, and it was very helpful. We appreciated that capability.
But again, when you go into a programmable logic environment, right, we're talking about different programming algorithms, VHDL versus regular C++. How did you negotiate all that? Was it a software environment that really helped you do that? So with all the trade-offs in hardware, programmable logic versus the fabric versus the ARM processor?
Well, we knew pretty much from the nature of the algorithms where they would have the best home. And I have this chart here kind of showing how you choose where the home should be for the algorithm. If something is fairly complex but low number of operations per frame, obviously it's easier to do it in C++ on the ARM. But other things that are extremely simple, like convolutional filter, but it'll run so much faster and better on the programmable logic. So we just made those judgments as we went, not with any particular tool, but just based on our knowledge of the algorithm. And sometimes we would switch things back and forth as we went along. So,
I guess one of the issues with going to a programmable logic is that you end up sacrificing power consumption, right, to a certain degree. So you find that you were able to optimize the power consumption of the algorithm, the power, by dividing it accurately between the two.
Yes,
software and
well,
hardware, right?
we haven't put a lot of time into really trying to reduce the power yet. This product, by the way, is not yet released. It's a beta product at this point, but we did find that the power consumption was very favorable. The camera we have there, it runs the entire processor, the sensor, and the infrared lights, and it's drawing 4 watts, maybe a little less than 4 watts. And we think we'll have it down to probably 2.5 watts before we're done for the USB 2 standard.
By the way, it's a Xilinx 7000 processor, in case you didn't guess at this point. So.
Right, 7020.
7020, right.
And we may actually switch to a 7010 at some point, but we want to start out with the 20. And so this just breaks down some of the processing in the programmable logic, the image filtering, contrast enhancement, Gaussian, Sobel, pretty much standard image processing stuff, and some of the eye-finding feature extraction is there as well. And then this is a close-up of the entire Xilinx, and down at the bottom you see the ARM9 cores there. We're only using one of the cores. But the key thing here is that they both have high-speed access to that memory, and so they can really share their results and work back and forth very easily together. So yeah, in conclusion, it was great to have that flexible boundary, and we got to actually a working system that was running and tracking at a reasonable rate very rapidly, mainly from the help of having the ARM processor in there. And then over time, we've been able to shift and implement the new algorithm in the programmable logic.
Yeah,
thank you.
Can you scoot back over a couple of slides to the components? Back up again for a second. The component layout of the board. There, back there. Yeah,
okay.
Back down. Down again. One more. Back down. There you go. What image processor do you have? Image sensor?
Oh, that's an Aptina AR0330. Is that right? Yeah. And we were familiar with that. It was a high-speed sensor, and we wanted the high speed, and we had used that. We liked the pixel size too, pixel size choice is important because that kind of dictates the size of your lens to some degree and how much light, the light sensitivity and so on. You make it too small and you don't get the sensitivity you need, too large, and your lens has to be too large. So the 2.2 microns was good. The support from Aptina was good. And I mean, you could use other sensors, but this was our choice.
Can you disclose some of the issues they had picking a sensor?
Well, we initially picked one that we thought we were going to go design with, and when we went down that road a ways, then we found out the manufacturer wasn't really going to produce that sensor. I think they were waiting for a large order or something, so we had to back up, and then we went with the Aptina sensor.
So don't go too far with your supplier, I guess, right? Be careful. Quick
Be
question
careful.
on the relationship between you and Xilinx. How did that help with the development of the design?
Maybe Bill would be a better one to ask.
Sure, we were able to work closely with Xilinx. We got Avnet, our supplier, a distributor involved, and they were able to bring in key Xilinx people to help us understand what it is we were trying to do and how best to utilize their tools and the device. And they were very helpful in making sure we had the resources needed to bring this product to where we're at today and to market very shortly.
Yeah, that's interesting. Okay. So how soon will the iTech be available for the mass market?
This should be early next year.
Early next year, okay. Roughly how much? Any idea yet?
How much?
How much, yeah.
Oh boy, I hate answering that question. Eye tracking, just to give you an idea of cost, eye tracking has traditionally been very expensive. When we first started in this business, they were $20,000 on up, and they're still typically a few $1,000s. And it's not so much because the hardware is so expensive, it's not. It's because if you only sell a few hundred a year, you have to charge that much. And eye tracking has been in these niche markets for decades. But now there's this movement and this interest to move it out into other areas. So hopefully we'll be able to sell these for $100 a piece, but we've got to find the right partners and customers at some point.
Right, so as you bring the cost down and you bring the power consumption down, what's the potential for this on the overall mass market?
Well,
What further applications do you see?
I kind of see three stages. The old market is the niche market, disability research. Then there's industrial applications in perhaps kiosks and aircraft, things like that. And then I see ultimately the consumer market could be in video games, could be in tablets, could be pretty much anywhere. So there's huge potential. It's part of the natural user interface revolution. And yeah, sooner or later it's going to be there.
I guess it depends on the sensitivity of the device, to what degree it can detect eye movement, right? Is it a resolution thing in terms of limitations?
Yeah, eye tracking differs from, say, gesture and face tracking in that you've really got to have better resolution to do it accurately. You have to measure features on the eye that are a fraction of a millimeter, and so you have to have a different lens. You typically need infrared, and you know it's a little trickier and can be a little more difficult than some of the other technologies.
So how does your algorithm work?
How does it work? Very well.
Okay, thanks, Rob. Good job. Any questions from the audience? Oh, you're really good, Rob. Okay, good job. Okay. Next up is Ian Johnston, and Ian will give a quick rundown of how the ISD Net series of surveillance cameras works. Can you pass around the board, Rob? The actual device?
Oh, sure.
Yeah. And maybe explain quickly how it works, the two IR sensors.
You want me to explain quickly?
Yeah, quickly how it works with the IR sensor.
Okay, we'll pass this around. So this is a complete camera, and it's got the infrared illumination as LEDs with the camera in the middle. There's also a filter that blocks visible light, passes infrared. And then this is just the processing camera board.
Okay, right. Thanks. Ian, go ahead. You got it.
Well, thank you. It's great to meet you all, and we'll talk about the exciting world of security cameras. Dan, if you can actually pass out this, so here's the final product, if you just want to pass it around it. Yeah, exactly. So one of the challenges that we had within the physical security world is scalability. Cameras are getting kind of more ubiquitous, and trying to get all of that video and all that processing power to one localized server is very, very difficult. The servers become overwhelmed, especially as resolutions now are increasing. It used to be that VGA and D1 or analog resolution was the most popular. Now 720p, 1080p, and even 4K is actually getting quite common. So servers are getting overwhelmed, and really the only way to solve that is to start pushing some of this technology to the edge. So what we've done is we've actually we've created a number of products, all using ARM processors, and the first products that we came out with were really edge storage devices. So we had up to 0.5 terabyte of storage actually on the camera itself, which is a remarkable amount of storage. The next device that we wanted to come out with, and we were scratching our heads how to do this, was to actually how to put a lot of compute power at the edge as well, not just a lot of storage, but a lot of compute power. So this is kind of an overall high-level block diagram of the device. As you can see, we use a Xilinx, and we also have another secondary processor in there that we use for H.264 encoding and some other image sensor pipeline stuff. So we have a variety of different outputs on the side. We have a sensor and a lens. Interestingly, we use actually the same lens, or the sensor. It's the Aptina AR0330. It's a fantastic sensor. It really is, as it was described, the perfect balance of having a 3 megapixel high resolution sensor, but the proper pixel size that you can choose an appropriate lens and still have very, very good low light and performance. So here's some of the challenges that we had. So one of the things is, as we just talked about, video analytic processing especially does not scale well. It's kind of the bring your own beer problem. So if you bring 10 people over to your house and say, hey, we're having a party. If one friend doesn't show up with beer, it's no problem. You can share, you probably have enough. If 10 more friends show up and you don't bring beer, then you have a problem. Video analytics is kind of that problem. Customers will be sold on a system that has 10 cameras, 15 cameras, 20 cameras, and the system is architected for that amount of units. The challenge, though, is that the integrator or the customer wants more cameras. So now they start loading up the system with more cameras. They get 20 cameras, 30 cameras, and the server starts to break down. And so they have to buy another server. So it gets exponentially more expensive as things progress, or it gets worse from a performance perspective. So what we needed was to push a lot of this stuff to the edge. So for example, if 20 people show up and they bring beer, it's no problem. It's just a lot more fun. So CPUs also, and this is one of the reasons why we chose Xilinx. CPUs are very good, as was described before, at handling kind of intelligent things where it's trying to make behavioral decisions between one or the other. It can process information on that very quickly. But what it's really bad for is bit level calculations and matrix transforms where it's trying to do line speed data coming in. For that, you really do need hardware, and you really do need some sort of programmable fabric in order to get that done. The other challenge that we had, we wanted to support multiple OSs. So currently we do Linux, we do Windows, and we do Android for the camera itself. And as I kind of led, we found a better solution. It's Xilinx. Xilinx is the perfect marriage of having a very fast, very capable CPU with an incredibly fast pipeline into the fabric, which is basically your wish is its command. You can almost do anything in the fabric. It's actually spooky what you can do in an FPGA now compared to what 10 years ago.
Ian, I'm curious. So did you wake up one morning and say Xilinx? Or how did it come about?
Sort of. It's our friendly neighborhood AVNet guy. It's kind of the same some story. You're always looking. It's conventions like this where you're shopping around for different ideas and different processor technologies. And so what we talked about and basically said, hey, this is what we're looking for. And our Xilinx rep from AVNet said, hey, I got the perfect thing. And we got early access to the program. It was actually part of the beta program at that point in time. We at least could see the device and get data sheets and everything like that. And so we were actually so convinced right at that moment that this was the perfect solution that we actually started to design. We had enough information from Xilinx to go forward. We had the tool support at that time. There was dev boards available in limited supply at that point. And remarkably, when we actually got the first engineering samples of the chips, within like 19 hours, we plopped the thing down, soldered it on, and actually had a working camera in 19 hours with a brand new FPGA, which is just unheard of. So it was a remarkable experience.
So I guess Avnet gets a slice of the pie too.
Yeah, yes,
common
Avnet always
denominator
gets a
here.
slice of the pie. Distribution always wins.
I'm curious then, at what point did it hand off from Avnet to Xilinx in terms of tech support?
Sure, and it really is a combination of everything. So it's a multi-tiered approach. So for example, our Xilinx FAE is a very capable person, wonderful guy, and so he really kind of helped field some of the low-level tools, or high-level tool selection, what we were going to use, and really chip selection of which part we needed in terms of the sizing of FPGA. And then beyond that, so some of the new stuff from Vivado. So if you guys haven't seen the new Vivado demonstration by Xilinx in their booth, you really need to check it out. It's really, really cool. So once we kind of went past what our local FAE could support us with, we then got hooked into the support team at Xilinx and some of the management there. And we did a pretty good evangelical job, I think, of explaining what we wanted to do. And they also embraced the vision of what we were trying to do. So we worked together as a common partners to get it to market.
Okay, good. Good teamwork.
Let's see. So one of the other nice things about choosing Xilinx and a really strong player in the market is that they have a roadmap of solutions that we can follow along, and our products will only get better, and the tool support will only get better. So it's always been good. So the two main system boards that we have here. So so this is here you go. So what we can do is this, if you just kind of hold it up to show the general size of it, then maybe the other one is probably a better, so this is it here. So, so if we go back to the other slide, sorry.
Yeah.
So here, so what we have is on the Zinc side, we have a 7020 Zinc. And we put a full gigabyte of RAM on this thing. So one of the challenges that we have as a hardware manufacturer and as a partner, and I'll say this kindly, analytic companies programmers are typically pretty lazy. You know, they have a full Pentium in front of them. There's 16 gigabytes of RAM, huge hard drive. So they imagine and come up with all this wonderful stuff. And then the embedded guys have to kind of scratch their heads and try and figure out how to actually shoehorn it into something that doesn't run on 150 watts. So one of the things that we did was memory consumption typically is kind of a stumbling stone for a lot of people. So we put a full gigabyte of RAM inside the processor. Fortunately, with ARM, you can get a very, very fast processor without a lot of power consumption. They've done tremendous work, especially with their dominance of the consumer electronic industry, to get a very, very fast processor within a very small device, small package that we can use, plus a low power consumption. We have NAND flash, and then we also have, interestingly, we have actually 2 gigabit PHY or Ethernet PHYs on this device. So on the other side, so we actually have integrated H.264 engine. It's from Ambarella. You know them from other companies like GoPro, DirecTV. They're very dominant in the world of H.264 encoding. It's one of the best video processors you can get. What else do we have that's interesting? Flash, DDR, kind of all the normal stuff. So the camera itself has RJ45 power over Ethernet connector. So that's how the normal security IP cameras work, then how they communicate generally. We also are a hybrid camera, so we actually have analog video that's supplied alongside the IP video, and that's an interesting use case for a lot of customers. The auxiliary power, so you can actually plug it in, 5 volts. The camera itself with the Zinc and the Ambarella running, it's 5 watts, so it's relatively low power for what horsepower we have in that. And we also have onboard storage on the device. So with 2 micro SD slots, you can actually put 128 gigabytes of storage in the camera, and then our other device you can put storage on. It's up to half a terabyte of storage. So this is a little bit more of a granular view of how things are connected. So effectively, one of the things that we needed to do as well is we wanted to sprint to market with this, and we actually we did this in concert with another big, large customer called Microsoft. They were very intrigued and interested in running Windows Embedded Compact 7 actually on the camera itself. All the video encoders in the world, they're all running Linux, and so they weren't terribly happy about that. They wanted a Windows solution. So we had, this is one of the areas of how fast this went to market. We had an idea in November, kind of one of those things that went, oh, we really need to do this. And we had the ability then, it was a concept in November. We actually, with Xilinx's help, with Avnet's help, and with thanks to the chip that just came up, we actually had the thing in their hands at the end of February for a conference that they were doing, and we actually were at a trade show with it in a productized form by the beginning of April. So we ended up winning 2 awards, Best Product of the Show and Best Megapixel Camera of the Physical Security World, which 2 huge awards. I was blown away that we got that. But regardless, it was thanks to Xilinx's all of their hard work and all of what they've done with the processor. You know, it was remarkable how easy it was to adopt. So basically the 2 main functions, so you see here, I've just kind of grayed everything out. You look at the main processor and the encoder. So the left side, the encoder, the main processor is the ARM. It basically can run Windows Embedded, plus Zinc and or Linux and others. So for that, we're using that side of the processor for analytics and processing and doing all sorts of wonderful things there.
I'm curious, what
Yes,
processor did you use prior to this?
So it was an ARM, but it was an ARM 11. So it was an ARM 11. It was still a very fast processor, but one of the challenges that we had actually, and one of the reasons that we did this architecture is, as has been talked about before, video data coming out of the sensor, it's just a fire hose of data that's coming from the sensor. I mean, we're pulling the 3 megapixels at 60 frames a second out of the sensor raw. And so one of the challenges is that really works memory. So the ARM 11, the arbiters of the memory bus, of course, gave preference to the H.264 encoder and the noise reduction that they had in it. And so the ARM 11 was basically starved. It couldn't get out to the memory. So what we wanted to do is create a separate partition, one for security reasons, for encryption and for kind of a firewall of duties. And then the other thing was with memory. The memory now, we put a full gigabyte of memory on this device, and we didn't want to hamper it with having to go out to memory for a lot of just house cleaning work with the sensor stuff. Now, one of the things that is possible, thanks to Zinc as well, with some of their multi-port memory controllers, is you can actually have multiple memory ports coming out to the device. So we could, in fact, partition the same thing with Zinc, move everything into the Zinc, and not run into that problem with the ARM. But it was just a simpler design, and we were able to sprint to market with that. Thanks. So one of the one of the advantages of smart cameras is now they can become far more autonomous. They can actually be in control of their own destiny. They're not just waiting to be talked to and knock on the door and then start spewing video. They can actually intelligently interact with the world, either doing eye tracking software as has been demonstrated, or just simply looking for bags that have left behind, humans, or people speeding through a red light camera, that sort of thing. It can all be done now at the device, which is very, very powerful. So the other challenge that we had from ISD is we want to be a really good playground for other people to work with. So we can't imagine, just like a smartphone, Apple couldn't have imagined, or Google could not have imagined what people will do with the phones and with the applications. So by creating an open and environment that they can actually run their stuff on, then you're basically free to come up with all sorts of ideas, get the code, get it actually running, work it on the camera, and then be self-sufficient that way. So in summary, for ISD, what we want is power at the edge, storage at the edge, distributed processing at the edge, and everything becomes far more scalable at that point in time. So we don't have to sacrifice the quality of a video camera. We can keep it to be 1080p 30 or even 4K without having to cut corners in order to make the processing work. So the other thing, I mentioned this before, but Zinc and Xilinx are really true partners kind of for the long haul with what we're doing. They have a roadmap for the product, of course, and we're able to follow along with that roadmap and provide voice of customer back to Xilinx. And that's one of the things as well that's actually quite refreshing. Xilinx has really been listening and asking questions about how we're using it and what we're trying to do so that they can make sure that future devices and future products will still work for us and actually will make the products better. It's very refreshing to see that happen.
I'm curious, how long did you think it would take you to do the actual design, and then how long did it take you?
So I expected it actually to take about 4 months longer than what we did. We actually beat our time to market by a long margin. There was a number of babies born within ISD at that time, and the Net Series was born. And the day the boards arrived, my lead EE on the project, actually, his wife gave birth that day. So he came in that night to make sure the board got up and running and then went back to the hospital. So it was, fortunately, thanks to Xilinx, it came right up. Yeah, it was quite the adventure.
That's a great story. Any questions from the audience so far? Go ahead, sir. Yeah.
Sure.
The question is, can you please say how big your engineering companies were and how big your company is? Is that it? How big your engineering teams? Right, yeah.
So ISD is a relatively small company. We effectively had 4 engineers running on this project. So.
We're a small company also, 11 people, and more than half of that is engineers, and most of them were on this project.
Anybody else? Go ahead, sir. Yeah.
What is the utilization of your Xilinx chip, and also what is the challenge in this project to get it to the performance and video capture you have?
Sure. So one of the ways that we were able to sprint to market was that we actually used a lot of a design reuse of a lot of the stuff that we already had. So by keeping the video encoder the same, we were actually able to develop the camera and develop the system on a Xilinx dev board with our standard camera just with an Ethernet link between the two. And then this is just a collapsed version of what we did. So the Xilinx right now is, we're doing a lot of interesting things with the ARM and starting to play around with some of the fabric with pushing some of the DSP and math filters and some of the stuff that you can see in Vivado right now. So at the moment, the ARM processor is actually relatively underused. We're now opening it up to other partners that are currently working on it. So.
Anybody else? Anybody wondering how these devices actually came into being? A quick story for you, and then I'll turn it over to Rob. Anybody know the Fitbit? Put your hands up. The Fitbit device, right? The inventor of that, James, he was sitting on his couch one day and he was putting on weight. He was getting kind of lazy. He was playing the Nintendo Wii and he wanted to put sensors and MEMS together in a useful fashion. So he came up with a way to combine wireless sensors with MEMS, and combine MEMS with wireless sensors to invent the Fitbit. And he had wireless challenges to go along with that. So he ended up going to Nordic to help get the wireless get the wireless part done. But the key thing is that just sitting on the couch, innovation can happen just like that. So it's not really, you can't predict it, but boy, when it comes about, it's really interesting. So I think Rob has a better story than that, so go ahead.
Well, as I mentioned earlier, eye tracking has been around a long time, but just my own personal story is I came down with a repetitive strain injury in both arms. I had been working as an engineer doing a lot of software work, and so had this severe repetitive strain injury in both arms, which made me start looking into alternative computer input devices, voice dictation, these different things, and ultimately I wound up founding this company, iTech, and then the rest is history. So it was kind of my own personal, solving my own personal problem there. Yeah.
Thanks, Rob.
And
Ian?
I'm just a geek. So I just wanted to do it. I have a passion for photography and some of the stuff that's happening now in the consumer electronic devices. You know, the iPhone 5S is just an outstanding camera. And it's thanks to ARM and some of the spooky stuff that they're doing back behind with the image sensor pipeline. And the realization is that I can do the same thing. It's, you know, we're all using the same sensors, we're all using the same processors, and it's just the imagination and the spark, and really ultimately it's the decision to do it. I mean, it's at the end of the day, you just take a deep breath and say, screw it, I'm going to do it. So that's really the biggest barrier.
Any last minute questions? Anybody curious about the future of surveillance and being Big Brother and being watched all the time and security? And who's your biggest customer right now at the NSA?
Well, not that we know of. It's sometimes difficult to tell who your customers are because they just disappear into the void at times. But we're having a lot of luck with casinos, believe it or not. They have a tremendous desire, one, for behavioral tracking to see, you know, what's working within their security. They also have a tremendous desire and need from a regulatory perspective, so they actually have rules that they have to follow that define for them what their video surveillance needs are. So they're trying to meld and merge these two worlds of what their marketing guy wants with what their loss prevention guys need and what their lawyers need. And merging all those worlds into one device has been something that we've been very successful at.
I'm curious, we have smoke-free zones. Anybody here want a camera-free zone regulation? Hands up. Okay, thanks guys for your help here. That was great teardown. Appreciate it. Okay, give them a round of applause, guys.
Thank you, guys.